Alright, so in this video I'm going to be talking about the vector cross product. So the cross product is represented by a cross between the two vectors, and it is represented by this thing here called a 3x3 determinant. So a 3x3 determinant, which you will recognize if you're familiar with linear algebra. So if you have done matrices before, you will recognize what this is. If you haven't, I will explain it very briefly for you. Basically what we do is we're going to reduce this into a sum of 2x2 determinants. So basically we're going to grab the first element here. We're going to essentially just block this column and this row. And now what we're going to do is we're going to multiply I by the remaining column. So we're gonna make a determinant or a new matrix out of these two remaining columns. So we're gonna have A2, A3, B2, and B3. Now for the next one, we're gonna grab this one and we're gonna do the same. We're gonna block this column and that column. So let's say we do this, this, and that. And now the two remaining columns are A1, B1, A3, B3. So we're going to have J, A1, A3, B1, B3. Now this one is going to be a negative because the sign convention that we use for determinants is usually plus, minus, plus, minus, plus, and so on. So we always start with a plus here. So the first element is positive, second one negative, third one positive. And then we're going to add the kth component. So basically if we grab k here, we're going to eliminate this column, this row, and then we're left with these two. So A1, A2, B1, and B2. So A1, A2, B1, B2. And now each determinant is going to be evaluated in the following fashion. So we're going to grab our determinant, and we're going to cross multiply these elements. So diagonally across we're going to multiply them. So we're going to get A2 times B3. Then we're going to subtract the other one. So A3 times B2. So this is going to be the result of this operation. And we're going to do the same for each of these. So in the end, you can represent your vector cross product in the following way. So you're going to have A2 B3 minus A3 B2 times I minus A1 B3 minus A3 B1 J plus A1 B2 minus A2 B1 K. So this is how you go about actually calculating a vector cross product. Now, what does this actually represent? Well, geometrically, the cross product has two definitions. So, the simple one is the following, right? Let's say we have a set of axes, right, like this, so x, y, and z. So what will happen now is assume that we have two vectors. Let's say we have some vector coming in this way. Let's call it v, and then some other vector u. And then suppose that we make a plane in which the two of them are coplanar. Well, in essence, you can make any plane in which the two are coplanar, but not necessarily. So imagine that they're coplanar in some plane here. Now, when we calculate the cross product of those two vectors, what we're actually going to get is u cross v is a vector that happens to be perpendicular to both of those vectors at the same time. So basically this is a vector that is normal to the plane that is made by those two vectors. And it doesn't matter if the angle between those two vectors is not 90 degrees, it can be anything. We can still get a vector that is perpendicular to that. So this is a really nice application of that, and we will see how that can be used for finding normal vectors to a plane in a three-dimensional set of axes. But essentially this is what it is. And what we are going to do now is we're going to have a look at a very simple example. So let's say we have vector A equals to the following: 0, 1, 3, and then vector b equals to 0, minus 1, 2. So in order to calculate the cross product, we're going to do the following. So a cross b is going to be equal to the following. So we're going to start off with the first component. I'm going to do a very direct method here. I'm going to grab this. So basically I'm going to multiply this, subtract this. So 1 times 2, that's 2. Minus 3 times minus 1, so that becomes positive. So 2 plus 3, that's 5. So that's our first component. Now for the second component, we have 0 times 2, 3 times 0. So that's just going to be 0. And then for the third one, we're going to have 0 times 1 and 1 times 0. So 0 again. Now, if we were to plot this on a set of axes here, so x, y, and z, what do you think we would get? Well, if we try to plot these ones, we know that they're both 0 along the x-axis. This one is going to be 1 along y here, whereas the other one is going to be minus 1. So basically we have it here. And then this one is going to be 3, so, and then this one is going to be 2. So we have our vector b here, and then we have our vector a here. And you notice that both of these vectors are coplanar on the yz plane. So this would be the yz plane because they have no component along the x-axis. And it turns out that our vector a cross b only has a component along the x direction. So basically this vector is perpendicular to that plane, to the yz plane. So it is also perpendicular to both of those vectors at the same time. And the reason this might be really useful is because when we consider rotation about a point, then what we're actually doing is we're using the right hand rule, which says you grab your thumb and then you curl your fingers in the direction in which it is rotating. So basically if your arrow is pointing this way, then you, with your right hand, then you would be curling your fingers in this way, so the rotation is happening this way. And you can do the same pointing in the other direction, and then you have this. So we will see later on how this actually relates to the concept of torque in physics and moments in engineering, and that can be quite useful for defining rotations and rotational motion about points and all that. So this is why the cross product is so important. Now the cross product does have some geometrical applications, so in the next video what I would like to do is introduce you to some of the geometrical applications, and then after that we'll move on to the physical applications.